Hello, I'm Mrs. J, and today we're going to talk about section 4.5, which is orders of magnitude. And when we're talking about magnitude, it's one way of comparing the size. So if we have the radius of the universe, which is 10 to the 26 meters, and the radius of the solar system, which is 10 to the 12 meters, we could divide them to find out how much larger one is than the other. Remember, when you're dividing the bases, you subtract the exponents. So it would be 10 to the 26 minus 12, or 10 to the 14. Well, what that would tell us is that the radius of the universe is 10 to the 14 times larger than the solar system, or 4 orders of magnitude larger. What the magnitude means is you're counting, in this case, by tens. So it's 4 times larger in magnitude. Let's look at another one. The radius of the sun is 10 to the 9 meters. And the radius of a hydrogen atom, which is very small, is 10 to the negative 11 meters. To compare them, then, we can take the 10 to the 9 and divide it by the 10 to the 11. Negative 11. Same base, subtract the exponents top minus the bottom. A negative and a negative is a positive, so it's 10 to the 20th, which means that the radius of the sun is 10 to the 20th times larger than the hydrogen atom, or 20 orders of magnitude larger. Comparing these ones, whoops, down one. We would notice this one's already in scientific notation. We'd want to rewrite this into scientific notation. The decimal needs to go here because we need a number between 1 and 10. So we moved it 1, 2, 3, 4, 5, 6. So it would be 10 to the 6th. It will stay positive because this number needs to get larger. So when we multiply, we need the positive here. If we compare them then, 10 to the 10th over 10 to the 6th, we only need to compare the powers because notice these are the same decimal. So the only difference is how many powers we move it over. It's hard to read this one. Okay, so we have 10 to the 10th. When we subtract them, 10 to the 10 minus 6, or 10 to the 4th. So this first number is 10 to the 4th times larger than this one, or 4 magnitudes larger. Again, the same values, but we rewrite them so they're in scientific notation, which means the decimal would need to go between the 3 and the 2. Because remember, it's always a number between 1 and 10. In this case, we move the decimal 3 places. But this number needs to be negative because this needs to get smaller. Then when we compare, 10 to the negative 6 over, well, you should put the smaller value on the bottom. Since this one is also negative, this is the smaller value. 10 to the negative 6 over 10 to the negative 3. -3 minus a -6, because top minus bottom. Negative and negative is a +6 minus 3 is 3. So this number is 10 to the third times larger than this one, or 3 magnitudes larger. There's two different scales we're going to look at. One is an additive scale. When you're working with an additive scale, the values are, should have wrote darker, are evenly spaced. 2, 4, 6, 8, 10. They're broken down evenly. In a multiplicative scale or a logarithmic scale, they go by log, so the values are different. If we look at 2 on this scale, we would take the log of 2, get 0.3. So it would be here. And then the 4, log of 4, is 0.6. So it would be 10 to the 0.6 here. Log of 6 is 0.77 or 0.8. So it's a little bit before that one, right about there. Log 8 is at 0.9 here. And log of 10 is at 1. Notice they're not evenly spaced like they were up here. They're going by base 10s rather than by the numerical value. And so that would be the difference. Another example on page 246. Number 11. Which is an additive scale, and explain why, and which is the multiplicative. Notice the first one's going by tens, 10, 20, 30, 40, 50. They're all evenly spaced. But the bottom one is not. It's going by logs. And that's why they keep getting closer and closer together. Kind of like my when we counted by 2s. When we wrote it in the logarithmic scale, it got closer and closer together as it went to the end. So A is an additive scale and B is a logarithmic scale. Let's see how they got closer. An ant is roughly 10 to the -3 meters in length, and the average human is 1 meter. How many times larger is a human than an ant? How many orders of magnitude is a man larger, or a human? Okay, so we know the ant, 10 to the -3. And we know the human's larger, well, 1 because we know they are, but 2 it said it. So the larger one goes on the top. A human is 1 meter. But we need to write that in terms of 10 to a power. Well, remember that 10 to the 0 power is 1. So if it's 1 meter, it's 10 to the 0 power. So we take 10 to the 0 minus a -3. Or 10 to the 3. So a human is 10 to the 3rd times larger. We could even write that. 10 to the 3rd would be 1,000 times larger than an ant. Or it's order of magnitude is 3. So it's 3 orders of magnitude larger. Graph the following on a power of 10 logarithmic scale. So I put powers of 10. 10 to the 0, 1, 2, 3, 4, 10 to the 5, 1, 2, 3, 4, 10 to the 10. So 1 watt would be 10 to the 0 watts. Because remember, 10 to the 0 is 1. So this is where A would be. Now B, 100 billion kilowatts. We know kilo means 1,000, so we could put 1,000 here. So then we have 100,000 billion. Watts. Now we can change that to put the billion in there. So here's the 100,000. Then we need 1,000, million, billion. Which would be 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 10 to the 14. So there's where B would be. 10 kilowatts. Kilo means 1,000. So we add 1,000. 10,000 now. Which is 10 to the 1, 2, 3, 4. 10 to the 4th would be here. Last one is terawatts. Tera means trillion. So we have our 1,000. Then we have 1,000, million, billion, trillion. 6, 7, 8, 9, 10, 11, 12. Okay, they're all there. Trillion is 10 to the 12. So we have 12, 13, 14, 15. So 1,000 terawatts is 10 to the 15 and would be here. That's it. But if you have any questions, let me know.